Yeah, I should have pointed out, we could have done this for sodium also. So if we had a membrane that was only permeable to sodium, so using the same formula, let's just do it for, I'll take potassium out of here. Well, you know what? Let's leave it. This time it's going to be equilibrium for sodium. Same idea, minus 61.5 because it's positive 1 times the log of this ratio. You know what? We can just use this formula up here and save us a little bit of time. If you remember the concentrations, it was just flipped. So this is the log of, instead of 100 over 10, it's 10 over 100. And of course, this is going to reduce down to 0.1, right? So 1/10, which is equal to, if you take the log of 0.1, log, that's just equal to -1. So the magnitude of the effect here is going to be, well, this is going to cancel out, right? So we're going to have positive 61.5 millivolts across those two membranes in this case. And if you think about that just for a second, what's going on here? So the sodium will keep moving across the membrane. In the case of sodium, it's no longer bouncing off. Now it's moving down its concentration gradient. Potassium is the one that's going to be bouncing back. Doink. In this second example. So same idea, taking positive charge, moving it over to the other side, and again making this side a bit more negative. But look where we're recording from. We're still recording from the same setup. So that changes our sign here so that we're now having a positive 61.5 millivolts instead of negative. So again, voltage is relative. All right. Let's see where we are here. All right, so we've looked a little bit at equilibrium potentials, and we can calculate one for sodium. We can calculate one for any ion that we're working with here, sodium, potassium, chloride, all of that works. Now remember, just for chloride, we would have a minus 61.5 over -1. So really, it would become a positive 61.5. Pretty easy to deal with there. So let's think about this just a little bit further. Let me see if I can drop this in for you. I've got this on another computer, and I'm going to see if I can drop a figure in for us. Didn't know how much room I was going to need here. Oh, this is going to be helpful. So we just did a resting membrane potential for a couple of values for sodium and potassium. And these are equilibrium potentials. If we use physiologic values, we're going to come up with a slightly different number here. And I'll show you some ion concentrations, and we can talk about that a little bit more as we progress with this idea. So a typical resting membrane potential under physiologic conditions, so this is a real cell. Muscles tend to be about minus 90 millivolts. Neurons are somewhere in between that, between minus 90, minus 70. There are even a few that are close to minus 50. So we have quite a range here for resting membrane voltages here. Again, I know some intro classes teach you neurons are always minus 70. Well, that's just not true. It depends on the ion concentrations in the membrane permeability, and we'll understand that as we get a little further into understanding resting membrane potentials. So under physiologic conditions, and I can show you how to do the math for this, the equilibrium potential for potassium is on the order of minus 95 millivolts. And for sodium, we're really closer to about positive 62 millivolts. And again, I can prove that to you with some numbers here a little bit later on. So let's think a little bit about what this is really telling us. Well, what we're really getting out of this is the equilibrium potential is assuming that the membrane is freely permeable. So down here, these values are freely permeable. Well, up here, this is a real membrane. So freely permeable to potassium or freely permeable to sodium, one ion at a time. We can calculate an equilibrium for each of those. Well, comparing the equilibrium potential, so what would happen if the membrane were freely permeable to that ion, compare that to what we actually measure here, you can see that potassium is actually quite close. There is only a small difference between the equilibrium potential for potassium than for our actual resting membrane potential. Sodium, on the other hand, wow, it's way over here. There is a huge difference between sodium's equilibrium potential and our actual resting membrane voltage. That tells you something. So remember, we're assuming that this is freely permeable to potassium here, and that's the voltage we would see once we reached equilibrium. Well, this is an actual recording. Let's say it's minus 90, just to pick one of these. Well, we only have a 5 millivolt difference between the equilibrium potential and the resting membrane potential. That means these are very similar. There must be lots and lots of leak channels for potassium in that membrane that we're recording from, just because the equilibrium potential is so close to the actual recorded value. And you can also conclude from that that there are very few leak channels for sodium, right? Hardly any at all, because we're so far away. You can also think of this in a different way. What if we had regulated channels and we open them up? You can also think of this as a driving force. Another name for that? Electromotive force. And that's actually what's going to drive this ion across the membrane. If we opened up more channels for sodium, we have a very strong electrochemical gradient driving that sodium into the cell. But again, very few ions have to actually cross to produce a very large membrane voltage. Potassium, on the other hand, has a weaker driving force. It will cross. And if we make the membrane more permeable to potassium, well, we're going to see a very small change in the membrane potential. So let's start using some real values here. I'm going to steal a figure again and drop it in here. It's actually from an old slide that I've used before. And these are physiologic conditions for a particular cell preparation or in a particular physiologic systems. These will vary just a little bit, but the trends still hold in most cases here. So I've got a number of ions that are inside the cell. We're sticking with millimolar concentrations compared to the outside. And this is to indicate a cell membrane here. Well, sodium and potassium that we've been talking about so far, you can look here that there's a lot more sodium on the outside. It's about 10-fold higher compared to the inside. Sodium isn't absent from the inside. Potassium, we see a much larger gradient that would drive potassium out of the cell. Was that about 40-fold? Well, anyway, it's a very large effect. We have a bunch of other ions here: magnesium, calcium, there's chloride, and some others here. Well, these are either transported. Let's take calcium, for example. Look at this, it's 10 to the minus 4 millimolar on the inside of the cell. Well, that is actively transported outside the cell. It's going against its gradient to produce this. It's usually about 1 millimolar outside the cell. It varies by tissue, but all right, so calcium has a super low concentration inside the cell, and this will be important for understanding synaptic function a little bit later on. It's going to serve as a signaling molecule for exocytosis of the neurotransmitter. Chloride actually does play a role in our resting membrane potential. So I boxed off the major players here. Sodium and potassium, hopefully it becomes obvious that those are players, because we also have a transporter system here that's going to deal with sodium and potassium, right? Sodium out, potassium in. And it's about 2, well, we can barely do this here. I'll do this. 2 potassiums in for every 3 sodiums out. Well, that's electrogenic, isn't it? Right? So we're having this net removal of positive charge from the inside of the cell to the outside. And you're probably thinking right now, aha, that's the resting membrane potential. Sorry, it's not. This pump here, the sodium potassium ATPase, that contributes to the resting membrane potential. You're not wrong about that. But it's really on the order of maybe 4 to 5 millivolts from that. So that isn't very much of a contribution. And just to complete this little diagram here, we also have proteins. These are like cytoskeletal proteins, or we're going to see we have proteins in axons involved in transport from one end, from the soma down to the terminals, etc. Well, these also tend to have negative charges, and they can't get out. So these are impermeable, and they do contribute just a little bit also. But again, we're looking at the order of maybe 4 to 5 millivolts at most, depending on the protein content. So the resting membrane potential is really based on passive separation of charge. So the sodium-potassium pump, that, let me just, I'm going to put it over here, the sodium-potassium pump. Oh, let's be specific and call it an ATPase. That's for setting up our gradients. And also for stability. And by stability, I mean stability of those gradients. So if we have a lot of activity across, let's say, an excitable membrane like a neuron, well, we can start to disrupt the gradients. And the sodium-potassium ATPase actually is important under those circumstances to reestablish the gradients we need for our resting membrane potential. But again, they're not producing the resting membrane potential. They just contribute to stability. So let's start thinking about a real membrane and permeability. I'm just plopping figures in as we need them here. Let's see if this works. Yeah, put another one in here. Let's make that a little longer. Yeah, a little better. A little bit. All right, so we have a longer membrane here. Well, remember what I just told you about resting membrane potentials and distance from the equilibrium potential. So we know something about relative permeability of these different ions across the membrane. You know that a charged ion can't get through this membrane because this is the charged portion, right? This is lipophilic. The ion can't get through the lipophilic layer. So we have to have channel proteins in here to make this more permeable. Another way to think of it is this is the resistance in our electrical circuit here. We're going to alter resistance, permeability, by the number of proteins we have in the membrane that will let these ions pass through. And we can do this relative to sodium. I'm just going to make sodium channel yellow. And as you'll appreciate in a minute, I'm not drawing an entire channel. We'll just make that little line there be for, that's going to be a sodium leak channel, because this permeability is relative. So if we set this, use sodium as our sodium permeability, let's say that equals to 1. Well, let's consider chloride. Its permeability would be about 10. Potassium is about 100. So it's about 100 times, this membrane is 100 times more permeable to potassium than it is to sodium. That's why we're seeing our resting membrane potential so much closer to the equilibrium potential for potassium, right? It's not very leaky to sodium at all. We'll make chloride red, so we need 10 of those. 1, 2, 3. And I'm doing that just to give you a visual representation of relative permeability. Now, if I were to do potassium, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and etc. out to 100. So we're going to have lots more potassium leak channels in this membrane, 100 times more than for sodium. And just the color codium, that's going to be like potassium, and these were going to be chloride. But the other reason I bring this up, again, it's partly a pet peeve, I guess. In figures, diagrams, whenever you see leak channels, usually you see one sodium leak channel and one potassium leak channel right next to each other like that. And you start getting the sense that, wow, there must be about equal numbers of those, and there are not. And that makes a big difference in understanding the resting membrane potential. So I'll show you the formula for calculating a resting membrane potential. So we're going to use a lot of the same things we did for Nernst, the same factors. We'll assume 37 degrees C, so I'm going to go ahead and just simplify that formula for you. And we're taking the logs of the concentration gradients and also taking into account permeability. So let me just show you what that formula looks like. And it looks a little scary at first, but don't worry. I'll show you it's actually easy to work with. Let me get just a little bit more zoom going on here. All right. So this is just the voltage across the membrane, just like we were to record it with a voltmeter. And this is calculating it. There's our minus 61.5. And I'll just say that, well, we'll use an X again for times. You can use a dot. Log base 10 of our ratio. It's actually a pretty big one, so we get a big line going on there. Now we can use specific ions too. Potassium concentration. I'm just going to put a little I here for inside. In potassium on the outside. But we also have to consider how permeable the membrane is for that particular ion. We're going to add these together. So now we're going to do sodium. Same thing. In or out. We have permeabilities that we have to consider as well. And finally, chloride. Chloride we need to think about just a second here. So we do need permeabilities. Whoop, get my little P's in there for permeability. But instead of inside over outside, we're going to flip this ratio here to outside over inside. And the reason for that is chloride has a negative charge. So remember the Z that would be under here will be a -1. But we can deal with that since we're taking a log of a ratio if we just flip it. And hopefully when I did the equilibrium potentials for potassium and sodium, that flipping makes sense, right? If you have 10 over 1 and you take the log of 10, you get 1. If you flip that 1/10, take the log, -1. So it's just a way of dealing with this minus sign without having to do a bunch of individual calculations. And I will do one practice example with you, and I'm going to use those numbers that I have up in this figure, this illustration right up here. And I'm going to use 10 for chloride. Let's just call that 10 because it's right in the middle of that range. And just to show you how to do one of these calculations, and I've got some practice I'll post for you. So let's see here. We've got a resting membrane potential. Times this log. The ratio is the part that takes us a little time to calculate here. So the permeability for potassium, we'll use relative values. We're going to say it's 100 times more permeable than sodium, so we're going to use 1 for sodium. And using concentrations for potassium, we should get 140 off of that table, millimolar. We're going to add that to sodium on the inside. That was pretty low. We had 14 millimolar on the inside. Remember our permeability for that? 1. Let's just start giving myself a little more room there. And chloride, we're actually looking at the outside now, but we need its permeability. Remember we said it's about 10 times. Oops, you can't really see it, can you? It's about 10 times that of sodium. So we have 10 times chloride concentration on the outside. And using these values, whoops, it's 110 millimolar. That's not so bad. Same permeability, so that's easy. And that was about 4 millimolar for potassium on the outside of the cell, times 1. How much sodium did we have out there? About 142 millimolar. And chloride's going to have the same permeability. And it's the same on either part of the ratio because this isn't unidirectional. If the ion can move across the membrane in one direction, it can move across in the other direction. So we have to put this in both parts of our concentration. So it's only about 10 millimolar based on our estimates there. So I'm just going to go down. I'm going to focus in on this ratio first. So 140 times 100, it's about 14,000. We're just adding zeros to that. Plus 14, right? 1 times 4. Plus, just add a 0. 1,100 times 400, or plus 400, plus, that was 4 times 100. 142. 10 times 10 is 100. All right. So, what do we have here? 14. It's about 15,114 divided by 4 by 642. What's that equal? I'm cheating now. This time I did this already. So this is going to give us a ratio of 23.54. We're going to take the log of that ratio. So since this is an example, I'm going to show you the next thing we would do here is take the log. Oops, that should be a lowercase l, but that's okay. Log of 23.54. And I did the math for us there. It's 1.37. So we just did this whole big chunk of this formula. Now all we have to do is take 1.37 times minus 61.5. I'm going to go ahead and put this down here. Kind of crunched myself a little bit. Bad 6. And that should equal about minus, I think it actually came out to 83 point something. I'm going to round it to 84 millivolts. So that's what we would see with those concentrations and these permeabilities across the membrane. So this is an actual, how we would get a resting membrane potential And this is not using Nernst anymore. This is using actually the Goldman-Hodgkins-Katz equation. Lots of guys working on this. We usually just give the first guy credit. Sorry to the other folks. Goldman equation. And we're also simplifying quite a bit. But this is good enough for body temperature and to give us an idea of what the factors are that influence the resting membrane potential. And I think that's enough to get you started.